All right. Good afternoon or morning, whenever you're watching this. Today we are going to be talking about topic 6.4, and it should be rotational dynamics, not kinematics. So sorry for the typo there. All right, so we're going to talk about things that are actually rotating and they're changing their speed. So they're speeding up or they're slowing down. So let's think about Newton's second law. What we know from Unit 1, the translational version is the sum of forces equals mass times acceleration. So that's when you have a force applied to an object and it accelerates in a linear or translational way. But then when we talk about things that are rotating, we have to have a specific kind of force that causes something to rotate, and that's a torque. So instead of sum of torques or sum of forces, we're going to have the sum of the torque on an object equals, instead of mass, we're going to have this thing called moment of inertia, which we'll talk about more, and that has the letter I, and that is all about the distribution of the mass. So if you think about if you are holding on to a meter stick, okay, you can hold it about the middle and you could, rotate it back and forth. And it's not going to be too hard to rotate. Versus if you hold it at the end over here, it's going to be a lot harder to rotate, even though the same object has the same amount of mass. So the distribution of the mass in relation to the axis changes how something rotates. And then instead of linear acceleration, we're going to have angular acceleration. So this is the rotational form of Newton's second law. Okay. So moment of inertia, that is our capital letter I. The unit is a kilogram times a meter squared. And the moment of inertia is all about how easy or hard it is to get something to rotate. So, for example, if you had a big wheel, okay, and you wanted to get it to rotate about this middle axis here, okay, versus a really, really thin object that was really, really long and had the same mass, okay, and they were rotating about this central axis. If these two objects have the same mass, this object that has more mass further away from the axis is going to be harder to turn. So even if these two things have the same mass, let's say this is object A, the moment of inertia for A is going to be greater than, let's say this is object B. All right, so let's talk about for two different scenarios. So for point masses, that's going to be a small, dense object. We can use the formula I equals the sum, if we have multiple objects, of the mass times r squared. So m is the mass, and r is going to be the distance from the axis. So let's do an example. We've got two spheres, and these spheres we're going to consider point masses. Are connected by a 4-meter long thin rod of negligible mass. That means we get to ignore the mass of the rod. The sphere on the left has a mass of 5 kilograms, and the one on the right has a mass of 7 kilograms. So let's figure out the moment of inertia if the rod is spun about the center. So we're spinning about this axis right here. And then if we spin around the left end, so this will be our axis for part B. So for part A, both of these masses are 2 meters away because we know the rod is 4 meters. So I is going to be the sum of mr squared. So that's going to be the mass on the left, which has a mass of 5 kilograms, and it's 2 meters away, and square that. And then add that to 7 times 2 squared. So the moment of inertia is 48 kilogram meters squared. Let's do for part B. Now we're holding it around this 5 kilogram mass. I is going to be that 5 kilogram mass, but it's 0 meters away from our axis. So that whole term is going to be nothing. But then plus 7 times 4 squared. And we end up with a larger moment of inertia because that 4 is squared, 112 kilogram meters squared. So that's the situation when we have two really dense point objects. Usually we'll have an object like a cylinder or a sphere or a rod, and we're going to use these formulas, which are derived with calculus, to determine the moment of inertia. So for example, if you have a rod and you spin it around the middle, the moment of inertia is calculated with 1/12 mass times length squared, versus when it's around the end, it's a lot larger. It's 4 times as large as a third ml squared. Usually always you'll be given these on tests. So let's do an example. A pulley, which is a solid cylinder. Okay. And so a solid cylinder, if we go back here, here's our formula, 1/2 mr squared. So I equals 1/2 mr squared. We're told what I is, it's 2 kilogram meters squared. We're given the radius, and it's pulled by a string wrapped around the edge. The applied force is 20 newtons, applied perpendicular to the edge of the pulley. So first, what is the mass of the pulley? We're just using this formula here. We know that I is 2 kilogram meters squared equals 1/2 mass times 0.4 squared. Rearrange that and solve for mass. We get the mass is 25 kilograms. And now we want to figure out the angular acceleration of the pulley. So we're going to use the sum of torques equals I times alpha, because we're trying to figure out alpha. So what this picture looks like, here's our pulley. Radius is 0.4 meters. And we're applying 20 newtons perpendicular to the edge. So 20 newtons to rotate. This perpendicular part makes it really nice because when we look at torques, torque is force times distance times sine theta. Sine of 90 is 1. So it's just going to be force times distance for the sum of torques. So force times distance equals I times alpha. Force is 20 newtons times 0.4 meters away. Divide by 2 equals alpha, and that gives us 4